Well, thank you, Misha. Thank you, Martin. And it's really a pleasure to be here. It's my first visit to IMPA and first visit to Brazil. And, so far, it's been very interesting. And well, also, thus far, it's been a really interesting conference. And right. So I want to talk about Heegaard splittings. And, well, yesterday in the first talk, Chaim sort of introduced Heegaard splittings and, well, just a discussion of them. And Heegaard splittings were something that were introduced by Paul Heegaard in around 1898. He's a Danish mathematician. And so, well, I mean, sort of one of the fundamental problems in understanding Heegaard, about Heegaard splittings, is that if you have, say, a closed three-manifold, the question is, what are all the Heegaard splittings up to reasonable equivalence relation? And that's what, I mean, this lecture will be about. Actually, just as a way introduction here, that there's actually so basically two situations. One where there's the manifolds Haken, which has a pi1 injective embedded surface, and the manifold's irreducible. And those manifolds were actually studied by Johansson in 1990s, who made some serious progress on this question. And then later, in 2006 to 2011, Tao Li produced a series of three really quite amazing papers on the subject in the context of non-Haken manifolds. And so the goal of this talk is to give you some hints about how to push what Tao Li did a little bit further to give sort of, well, complete classification for non-Haken three manifolds, or more precisely, if you have such a manifold, just an effective algorithm for constructing all the splittings. And you'll see that this really demonstrates the power of minimal surfaces and geometric point of view to address problems in three-dimensional topology. So let me just give you some background and maybe just have some. So here's some background about Heegaard splittings. So if you have a three-manifold, then if you could just write it as the union of, well, two handle bodies. So this is just a solid donut of genus 3, and you take two such things, and you glue them together along their boundary. That's a Heegaard splitting. So here M is closed orientable three-manifold. So this is so some like very simple examples. Well, you could take the three-sphere and you could just write it as just a union of two balls, just glued together. And well, if you have, say, S2 cross S1, well, you could take just a solid torus and another solid torus and just glue it by the identity map, or just double the solid torus. That's S2 cross S1. And more generally, if you just, well, a lens space. So that's what you get when you take just more generally just two solid tori and just glue them together. So a basic fact is that every three-manifold has Heegaard splitting. And the proof is basically, well, due to Moise and a simple observation. So Moise, around 1958 or so, I mean, he showed that every three-manifold has a triangulation. And on the other hand, if you have a manifold with a triangulation, then there's a natural way of creating a Heegaard splitting. Simply, if you just take M, and you could just write it as a neighborhood of the one skeleton, well, union a neighborhood of, well, the dual one skeleton. So in this manner, just thinking up the one skeleton is sort of one of the handle bodies, and the complement is the neighborhood of the dual one skeleton. So the classification problem is this. So given a three-manifold, so list without duplication, well, all the irreducible Heegaard splittings up to isotopy. So what exactly does this mean? Well, to start with, I mean, a Heegaard splitting is just a decomposition of the manifold into two handle bodies. But just actually as a technical point, actually we'll think of a Heegaard splitting as sort of an ordered pair of handle bodies. So you can think of, well, you can think of the Heegaard splitting as consisting of this handle body and this handle body, where this one comes first. Or said another way, you could think of just the splitting surface with a normal orientation. So you know which is the H0 side and which is the H1 side. I mean, you could just as well do it without such things, but but for the purposes of this lecture, a Heegaard splitting is you can think of it as a surface with knowing which side is the 0 side and which is the 1 side. So isotopy, of course, just simply means up to just an ambient movement of the manifold to such splittings are the same. And irreducibility is to well, just to rule out sort of simple things. So for example, S3, as we just saw, is the union of just two three balls, but it could just as well be the union of two handle bodies of genus 2, or for every genus, just glue them together in the right manner, you get S3. And the point is that more generally, if you have some manifold and it has some Heegaard splitting, whatever it is, well, just by adding on sort of just trivial handles, then you can get sort of a splitting of one higher genus. So, well, you just add on sort of just a little sort of just trivial handle here, and just a little trivial handle there, and so now you've raised the genus up, and this operation is called stabilization, and the reverse operation is called destabilization. so a splitting is irreducible if you can't sort of destabilize it. So, right. So here's some just basic theorems in the subject, which is Waldhausen. So in 1968, he proved that the three-sphere has sort of a unique, well, Heegaard splitting. Well, again, I mean, up to stabilization and isotopy. And, well, on the other hand, Joan Berman, in, I guess, 1974, she showed that there exists sort of lens spaces with two splittings, with at least two splittings. So actually, what she showed was that for some lens space, there's a splitting where you can't reverse the sides. So there's certain lens space of a torus where you can't do an isotopy that sort of flips the sides. On the other hand, there's well, theorem of Bonan, O'Tal, and Hodgson, Rubinstein, 1982, which is that well, that lens spaces have a unique, well, splitting surface, splitting torus. I mean, what I mean to say is that up to isotopy and stabilization, that the only irreducible splittings are just this one there, although there's the question of sidedness. So anyway, there's been sort of a lot of work in trying to understand Heegaard splittings of various manifolds, and I mean, Seifert-Fiebert space pretty well understood by Mariah Schultens, and culmination of work of many people, and so these are just some basic results for sort of low complexity manifolds. Now, so I need to tell you sort of, well, actually, Chaim again sort of introduced this idea of strongly irreducible Heegaard splitting, and that's sort of based on this really sort of fundamental paper of Casson and Gordon. So in this remarkable paper, they introduced this idea of strongly irreducible splitting. So a Heegaard splitting is strongly irreducible if here's the gluing, here's the Heegaard splitting. If every essential curve here, every essential compressing curve here intersects every essential compressing curve there, that is, the boundary curves intersect. So every essential disk in H0 hits every essential disk in H1. And remarkably, this is actually a fairly common phenomena, as Klein remarked, and in part because they also proved in this paper, which is they also proved that that irreducibility plus, well, weak reducibility implies that the manifold is Haken. So something, if a splitting is not strongly irreducible, it's called weakly reducible. And if you have something that's weak, if you know that your manifold has a weakly reducible splitting, but which is also irreducible, then it turns out the manifold's Haken. And there's just a great many non-Haken 3 manifolds. And finally, well, they also proved that there exists a 3 manifold with infinitely many different strongly irreducible splittings. I mean, in fact, the genus of these splittings go to infinity. So, right. So this was the introduction of strongly irreducible splittings. And now I'd like to tell you about Tao-Li's theorems. So Tao-Li, as I said in the introduction, proved 3 remarkable theorems. So. Well, it's obtained by doing surgery on some pretzel knot. So, well, there's a certain pretzel knot that actually in this guy Louis Paris's PhD thesis he found that that had this sort of remarkable property that it has a sequence of incompressible spanning surfaces of genus going to infinity, and anyway, they do sort of some Dane filling on that to get a closed manifold, and somehow those surfaces correspond to, well, thickened up correspond to the Heegaard surfaces. So, okay, so Tao-Li's theorem. Well, he's proved actually other theorems, many other theorems that are great, but so in this context. So one, well, let me just say this is 2 parts. That is that, so here M is meant to be non-Haken. So for every genus greater than 0, there exists sort of constructible surfaces, say S1, S2, Sn, such that, well, constructible Heegaard surfaces, such that any irreducible splitting of say genus G is one of these. And the second thing is that well, he did this in 2006. Is that there exists an n positive integer such that the genus of any irreducible splitting is less than or equal to n. So in particular, a non-Haken manifold has only finitely many irreducible Heegaard splittings. In contrast, for example, in this situation here, where this manifold is Haken. So, just
these are strongly irreducible?
well, in the context of non-Haken, strongly irreducible and irreducible are the same thing. So, right, and let me just say in words that Johansen in the 90s more or less, proved this theorem for Haken manifolds. And, actually, what he proved was that if you're given a Haken manifold and a genus, there's only finitely many irreducible splittings up to spinning around an incompressible torus. So in dimension 2, if you have a simple closed curve, there's a diffeomorphism by just doing the Dane twist around the curve. And if you have a torus in a manifold, you could do a diffeomorphism by sort of spinning around the torus, so up to sort of spinning around tori, there's this finiteness. So just a historical point is in this is what's actually known as the generalized Woldhausen conjecture. Woldhausen conjectured that sort of there's only finitely many irreducible surfaces for the minimal genus splitting. And so put together, this is sort of a much stronger form of what Woldhausen conjectured in the context of splittings. So right. So this is what Tao Li proved. And so if you look at this, at first glance, it looks very much like just sort of the classification theorem that I asked for, because here for every genus he lists the Heegaard surfaces that contain all the irreducible ones, some finite set, and sort of has actually a bound function of the manifold which sort of bounds the genus of such things. However, there's some things that are missing. So to complete sort of this classification, or at least an effective classification, is one, sort of you need effective algorithm to compute this n. So his n comes from a compactness argument, sort of a limiting argument, and it would be nice to actually be able to nail down this n sort of in a finite manner. And the second and third problems are that the list of surfaces that Tao Li produces might have duplications. Conceivably, some of these surfaces are isotopic. And further, it's possible that some of these surfaces are reducible. So you need to figure out how to do that. So 2 is find sort of effective algorithm to eliminate duplications. And 3, you need to find a way to eliminate reducibles. So this is what I would like to explain today. So this is done with Toby coding, and these two are with Toby and Dan Ketover. So yes?
Toby says that these surfaces, well, it doesn't guarantee that it's irreducible.
No. He produces a set of surfaces and says, well, they're all Heegaard surfaces, and all the irreducible ones live there. But we don't know about. So actually, before I sort of just give you some hints about this, which just I'd like to make some preliminary remarks. And well, first of all, the proof of one here actually well, sort of gives sort of a simpler argument for the proof of these theorems there. However, it's hardly an independent argument because, I mean, we certainly rely on, crucially, and some key ideas that Toby proves. So I would just view it as sort of cleaning up the argument a little bit. And right, and the second thing is that Toby did all these theorems almost by bare hands. I mean, he just assumed the manifold was non-Haken and started with some triangulation, and worked, in a very, very hard and very, long and subtle arguments to produce these theorems. However, I mean, since the time of his work, I mean, Grisha Perelman proved the geometrization conjecture. So we can assume geometrization. And for a non-Haken manifold, I mean, non-Haken manifolds are either ciphered fibered spaces or hyperbolic. So as I mentioned earlier, that ciphered fibered space is more or less understood by Mariah and Schultens. So it suffices then to assume that the manifold is hyperbolic, and that's, of course, just a tremendous amount of structure, and so this certainly needs Perelman. So if you just include Perelman here, it's probably simpler just to do what Toby did. So right. So I'd like to just give you explain some of the ingredients that go into one, and then I'd like to give you some ideas of outline of how to prove 2 and 3. So So Chaim, in his talk yesterday, talked about a theorem that he stated with Pitts, which was in 1987, and that's going to play a fundamental role in part 1. So let me just state that. So here to start with, we're starting out with a 3-manifold which is hyperbolic. But rather than just using the hyperbolic metric, just perturb it a tiny bit, and so just give it a bumpy metric. So they proved that that a strongly irreducible Heegaard surface, there's two cases. Isotopic to, an index less than or equal to 1 minimal surface. That is, it's either a stable surface or index 1, or 2, after pinching, sort of an unknotted neck, then it's isotopic to a stable one-sided surface, one-sided minimal surface. So, they announced their theorem in 1987, but as far as I know, there's no sort of complete elaboration, exposition. But I need to say that that some very interesting partial results in this direction are due to Dan Ketover. So, for at least sort of something in this direction, you can find manuscript on the archive. So, I'd like to mention two important ingredients that are sort of central to what Toby and I did. So let me state them. Well, first is if M is hyperbolic and eta is between -1 and 0, then there exists finitely many eta negatively curved branch surfaces that carry all index less than or equal to 1 minimal surfaces. So in particular, they carry every up to pinching a neck. They carry all the strongly irreducible Heegaard surfaces. So let me just say a few words about this. Well, I mean the point is this: that if you have an index 0 surface, then Rick Shane tells us that the surface has sort of a bounded second fundamental form, so it doesn't curve too much. And on the other hand, if the surface is index 1, then I guess, work of Lopez, Roche, Cheng, Tisk, and various results of Colding and Minicozy show that, well, either the surface, again, has sort of a bound and second fundamental form, or if there's some spot where there's lots of curvature, then basically it looks like just basically sticking in a little catenoid. There's this little catenoid, and then away from that, away from a neighborhood of that, then there's not much curvature. So in other words, I mean, using these results in minimal surface theory, that says that more or less all the surfaces of interest don't curve too much except for at most one spot where the topology is pretty standard. So this theorem simply says that, well, the totality of such can be organized in a reasonable manner. So I mean, without knowing what a branch surface is in one dimension lower, if you have a curve and it's spinning around something and then spirals out, well then if you sort of step back, well, it looks like it's sort of, well, such a thing is carried by this train track. So you just sort of squeeze the things that are parallel together. And so a branch surface is just a one higher dimensional version of that. And the second ingredient is this. So again, which is that, well, there exists a polynomial P such that the growth rate of any surface, any closed surface, carried by one of these branch surfaces, well, finitely many, by one of these BIs, is bounded by P. In other words, if X is in this surface, then if you look at the ball of radius r about X, the area is less than P of r. So actually, this is really Planck's theorem. Planck showed that if you have a foliation, sort of measured foliation, then the leaves of measured foliation have polynomial growth, and this is just Planck's argument in the context of branch surfaces. Though I should point out that these branch surfaces typically carry planes. So it's crucial that the relevant thing is surface. Actually, any measured lamination would do too. So the point is you have these branch surfaces that on one hand, the stuff it carries have polynomial growth. On the other hand, it's carrying these index 1 surfaces, which have, I mean, the curvature is, say, approximately -1 or less. So as we know that growth of a negatively curved surface grows exponentially. But on the other hand, since it's carried by the surface, it's growing polynomially. So therefore, this forces a bound on the injectivity radius of any surface carried by these branch surfaces. So anyway, that's a crucial thing, that these branch surfaces with a bound on injectivity radius. And so therefore, if you have a complicated Heegaard surface that's carried by branch surface, you see genus, or at least topology, appearing, at some definite periods. So, and that finiteness point actually is sort of the crucial thing to making sort of an effective version of Talley's work.
Does this imply something about laminations or something about carrying the branch surface?
Yeah, so if you have, I mean, this says that any measured lamination has polynomial growth, but laminations that aren't measured, like, there's no information. So, right. So anyway, I just want to give you a hint as to how geometry plays sort of a huge role in sort of establishing a sort of a finiteness fact, this injectivity radius bound, which is crucial here. I mean, actually, what Talley proves is that if you say fix a genus and you had, say, infinitely many irreducible splittings, then, well, actually, rather scratch that. If you suppose there's just an infinitely number of splittings where they're just going off to infinity. I mean, again, Talley proved just that, again, well, first, is that there's only finitely many relevant branch surfaces. And he took a limit of these surfaces that were carried by this branch surface and got a lamination and showed that this lamination was incompressible, so therefore it's approximable by an incompressible surface. And that showed that this manifold was Haken. I mean, here in these Casson-Gordon examples, we had infinitely many strongly irreducible splitting surfaces, but turned out, I mean, actually, they're in it's in a Haken manifold. Okay, so now I want to give you some ideas of the proof of these theorems. So here's the question: how to decide if strongly irreducible splittings or splitting surfaces, say T0 and T1, are isotopic. So this is what I explained. This is what work with Toby and Dan Ketover. So that's what I want to explain now. So at least give you some hints. Okay, so T0 is a Heegaard surface. So therefore we can think of it schematically as this. Here's T0. T0 bounds two handle bodies. Say there's H0 on this side and H1 on that side. So H0 is a handle body. So therefore it has a one-dimensional spine. So right here is sort of a one complex, as is here. So from this surface to this one complex, you could just fill it in with a foliation, and you could fill it in with a foliation there. So you get a Heegaard foliation of, so let's call that the Heegaard foliation. And I guess Joel and Abby Thompson, Bill Thurston used Heegaard foliations to do very interesting theorem about stabilization. But so here we look at this foliation. Now, on the other hand, if we have T1, so it also has its one complex here, one complex here, and there's the Heegaard foliation for T1. So suppose T0 and T1 are isotopic. Well, then we could sort of fill in this a square with foliations, well, with Heegaard splittings or Heegaard foliations. So if T0 and T1 are isotopic, then we have this Heegaard foliation here and this one there, and we could do sort of an isotopy and get from here to there. The question is how to figure out whether such a thing exists. So here, let me just point out the difficulty in this whole issue, which is if we look down at this level, we have a 1 complex here and 1 complex here, and we could just move along by 1 complexes to get from here to there. Somehow, just nice sort of isotopy and maybe sliding arcs over other arcs, and we get from here to there. But the problem is such a process could be extremely complicated. On the other hand, we could somehow maybe just go through the middle here, but maybe the surfaces that you go across, maybe the areas have to get fantastically complicated. So somehow, a priori, how you get across, there's lots of complexity. So now the point is that the miracle of min-max is that you can sort of bound the complexity of things. So right. So what do I have here? I have a function f from t cross I into m, where f, say, restricted to t cross s cross I, that's the, whatever, that's the S Heegaard foliation. Yes? Okay, so we have the square, the square of surfaces. Now, so that's step 1, just this picture here. So step 2 is use the min-max theory to extend, well, f restricted to, well, t cross boundary of I cross I. In other words, the boundary of this square, well, to extend the function restricted to the boundary to a new function, h, mapping t cross I into m. Well, with the following property, such that for every s and t, well, the area of, well, t sub st, the t cross s cross t, is less than or equal to the max of 2 pi plus epsilon times the Euler characteristic of t, or the area of a leaf of H0 or H1. So in other words, using sort of min-max theory, you can just sort of rip out this stuff and put in sort of a new system of surfaces in the interior, such that the area of any of those surfaces is not any larger than the maximum of either the area of one of the initial foliations, leaves of the foliations, or more or less 2 pi times the Euler characteristic, which is the area of the hyperbolic surface. So, right. So note in particular, this number is this number is a function of the initial data, because you know the initial foliations, you know the genus of the surface. So, right. Okay, so here's step 3. So step 3 is that suppose that the injectivity radius of T0 and T1, which we know explicitly to start with, is bigger than 8 times delta, where delta is less than the injectivity radius of M, say, divided by 16. Then there exists an isotopy from T0 to T1 such that 1 is that the area of the surface T sub T is bounded by this constant C, and 2 is that T sub T has no essential curves of diameter less than or equal to delta, well, which compress to one side or the other. So in other words, step 3 says I could basically give a bounded geometry isotopy from T0 to T1. It's the control in the area is sort of uniform by C, and furthermore, it doesn't have any sort of short curves that are compressed to one side or the other. So notice if you're down here in this region, if you're just like right over here, then you're right next to a 1 complex, so you have like extremely short curves that compress to this side. If you're over here, you have extremely short curves that compress to the other side. So the claim is I can control the area and the curves can't be too short. So the proof of that is sort of just staring at this picture here, because here we have sort of this green zone, where here, sorry, here I've this square over here is meant to be the square coming from step 2 from the min-max surfaces, and so here this green zone, this corresponds to surfaces with sort of delta short curves that compress to the H0 side. On the other hand, up here, again, there's sort of this 1 complex, this sort of isotopy of 1 complexes, and here there's sort of this red zone. This is the region where you have sort of delta short to the H1 side, and the point is that you can't have sort of the red zone intersect the green zone, because if you had sort of a really short curve that compressed to one side, if you had a point here, that would mean that there was a short curve that compressed to one side, but somewhere else there's a short curve that compressed to the other side, and that shortness is sort of way shorter than injectivity radius, and you can use that to find actually disjoint curves that compress to one side or the other. So the point is that if the red intersected the green, then you'd be weakly reducible. So the proof is sort of the red intersect green. It's non-empty implies, well, T0 is weakly reducible. So therefore, we can find a path in this square that goes from one side to the other. So this is our isotopy. So, whoops. So, right. So, right. Okay. So step 4 is construct a graph G such that well, the vertices are a finite net in the set of surfaces with sort of this bounded geometry. In other words, the area is bounded by some constant and doesn't have sort of short curves, short diameter curves that compress to one side or the other. And edges are sort of nearby surfaces, nearby vertices are sort of connected by an edge. So, and finally is step 5, is that T0 and T1 are isotopic. Well, if and only if they're in the same component of this graph. So I've run out of time, and the point is that, I mean, this is all in this sort of the smooth category, all this discussion, but the fact is that T0 and T1 are, say, normal surfaces to start with, and you can, well, approximate this triangulation, this path by sort of an isotopy of surfaces that intersect some particular triangulation in some reasonable manner. So, well, we call such things like crudely normal surfaces and crudely almost normal surfaces. Anyway, and the totality of such surfaces is finite and you know, innumerable, and there's sort of elementary moves to get from one to another. So that's this graph we're talking about, and well, I mean, this construction here will show that, well, that T0 and T1 will be vertices of this graph, and this isotopy gives a path in the graph from one to the other. So anyway, I'm out of time, but in this manner, we sort of we eliminate duplications. And let me just say, in 30 seconds, is in the context, how do you eliminate, well, decide whether something's reducible or not? Well, in that case, if something's reducible, then it's isotopic to something which is obviously reducible. By which I mean, if you just look at it, you could just see that little tiny handle that's sticking out. So in that situation, well, in that situation, again, we construct sort of the green zone and the red zone. But in that case, there's the surface in question here is I mean, if this guy is reducible, then there's a guy over here which is obviously reducible, and where the green zone and the red zone cross each other. So, so therefore, you could find, starting here, you could find an isotopy to some spot where at the scale of like 2 delta, it compresses to, there's a 2 delta diameter curve at most, one that compresses to one side, one compresses to the other. But on the other hand, nothing of size delta compresses to either side. So I mean, it's a little bit more subtle, but again, you can construct sort of a graph, and certain vertices will consist of obviously reducible surfaces, and well, so you eliminate the reducible ones by just looking at this graph and your original surface, and you identify the obviously reducible ones, and you'll be reducible if you're in the same path component as an obviously reducible one. So anyway, thank you for your attention.